Good evening, Internet. I am Matt Buyak, and this is the first of several videos dealing with big integers. That is, those integers larger than 2 to the 64th power. So in the last video, we found a solution for the 19th problem from the Project Euler problem archive. And I mentioned that in this video, we would be moving on to problem number 20. However, problem 20 asks us to calculate the number 100 factorial, which is a little bit outside our current capabilities. That is, C and C++ have native support for integers up to 2 to the 64th power, but 100 factorial is much larger. And this is actually an area where some other languages like Java and Python are much more capable than C and C++. In fact, many modern languages have either native support for big integers or have a standard library for working with big integers, and C and C++ have neither of those. Even so, there have been several problems in the past where we've been asked to work with big integers. Most recently, problem 16, but also up here, problem number 13. And we've always been able to find some amount of cleverness that would let us avoid tackling the problem head on. But eventually, we're going to need a robust solution. And so the time for that has come. Now, as a brief aside, in deciding what we're going to put in our big integer class, we might take inspiration from the operators that are supported for native integer types. And just scrolling down here through the Wikipedia article, you can see that there are quite a few. Most of these operators are operations on the integers. And so if we were to implement all of these in this video, the video would be 4 hours long, and everyone would fall asleep and unsubscribe. And so rather than that, we're just going to implement the functionality that we need for the particular problem we're trying to solve, and in that way, over time, develop a fully featured big integer solution. Okay, so looking at problem 20, what is it that we need to be able to do? So first, we need to be able to calculate the digits of 100 factorial. And this is a problem we've actually already solved. In particular, in problem 16, the problem that I mentioned previously, we had to calculate the digits of 2 to the 1,000th. And so we can adapt our solution to that problem to form the core of our big integer class. We also have to be able to calculate 100 factorial, which involves multiplication by small integers. And this we did not implement for problem 16, though it would have been useful. We actually found a trick to let us construct 2 to the 1,000th without doing multiplication. And so we will need to implement that for problem number 20. So the plan is, in this video, we're going to look at calculating the digits of a number and adapting our solution from problem 16. And in the next video, we'll look at implementing multiplication. And so we'll have the tools necessary to solve problem number 20. So let's get into it. We'll need to create some new files to hold our big integer class. You may recall from my series on prime numbers that we have this libnumtheory library that lives in our common directory. You can see here the primes files. And so we're going to put our big int class in the same place. So we'll say bigint.h and bigint.cpp. And then we'll also want to take a look at that problem 16 solution that I mentioned. Now, in writing this solution, we actually did a fair bit of analysis. So I would recommend, if you haven't seen that video, maybe go back and take a look at that. I'll put a link in the description. But the general idea of our approach is that we're just repeatedly dividing by 10 and taking the remainder. And so that's what we're going to be implementing for our big integer class as well. In addition to doing division and finding the remainder, we also need to be able to check whether or not our integer is 0, and we need to be able to write to an arbitrary cell in our big integer. And so, keeping that in mind, let's put together an outline of our class. So we'll say class big int, public, private. And so under the public section, we'll have a constructor, big int. And as I mentioned, we need to be able to check if our integer is 0. We also need to be able to divide and take the remainder. So we'll say uint32t divmod uint32t divisor. And also, as I mentioned, we're going to need to be able to write to an arbitrary cell. And so one approach is we could just make our cells, we could put our cells up here in the public section. But that's generally considered poor design. We usually want to put our data under the private section and add accessors up here. And so we're going to say uint32t read cell, and it's going to be index, and then we'll want write cell, index, and uint 8t val. This should also be. You'll recall that our cell size is an 8-bit integer here. Okay, so we'll also need to obviously move over our cells here. And we'll need this constant here. And we will need to include standard integer. And actually, we will want to change these to be 8-bit as well. Yes. Okay, so that's a good outline for our class to start. Let's see if we can fill in the implementation. Okay, so going back to our problem 16 solution, you'll notice that we didn't initialize these to 0. And that's because it's a global variable, and they're automatically initialized to 0. That's not true, however, of class members like cells here. And so we'll need to manually initialize those to 0. And we'll do that using memset. So we'll say address of the first cell. We're going to write zeros. And the number that we're going to write is just going to be num cells. But let's actually, I'm going to rename this to be num big int cells. Okay, so then we'll say num big int cells. All right, so that should be all we need for our constructor. Let's go on to our 0 here. Okay, so to determine whether our big integer is 0, we just need to iterate over all the cells, and if any of them are non-zero, then our big integer is non-zero. And so we'll just say for uint 8t cell in cells, if cell is non-zero, then return false. And if all of them are 0, then return true. This is the, if you're not familiar with this, this is the for each syntax. Just iterates over every element of cells and checks to see if it's non-zero. You'll note that this is possibly a little bit inefficient. Going back to our problem 16 solution, we'll be doing this check in every iteration of our while loop, and so we basically have a loop within a loop, and that can always get a little bit inefficient. So we want to be careful about that. And so let's just make a note to ourselves here. To do optimize this later. Okay, so moving on to Divmod. So you might wonder why it is that I've made this a single function. After all, the standard integers have separate operators for division and calculating the remainder. But it's really the same algorithm for both, and so and often you want both, and so separating them means that often you would end up running the same algorithm twice if you want to get both the remainder and the quotient, and so I've just combined them into to one. Okay. So this is going to be the heart of our implementation here. So we're basically just going to copy over this whole thing here, and then cut out what we don't need. Okay, so first of all, our original implementation here is looping over. It's doing the division multiple times, and we only want to do one division, so we're going to cut that loop out. We're not tracking the sum, so we want to cut that out. We're not returning 0. We want to return the remainder. We don't need 0 there. We don't need sum. We do need to initialize our remainder to 0. Let's see, that should be everything we do need I, we do need remainder and bring down, and we do need our accumulator. So the rest of that should be required. We also want to be sure that we're dividing by divisor instead of just hard coding the value of 10. Oh, and we don't need to update our 0 tracking there because we're not doing that here. Okay, so that should be it for our Divmod. We also, in anticipation of implementing these two methods, want to be sure to use them here. And this is just a principle of good design, is that if you're accessing a class member from within the class, and you have some kind of special accessor that does maybe bounds checking or memory management or whatever in response to those read and writes, you want to be using those internally also. So we're going to say read cell I, and then here we're going to say write cell I, comma, that value. Okay, and now we can implement these. Okay, so read cell is just going to be, well, first we can actually do some bounds checking, as I mentioned. So we can say, if index is greater than or equal to num big int cells, return 0. So not only does this protect us from reading out of bounds, it also makes logical sense. That is, if you had the number 5 and you were trying to read, cell number 300, well, that digit doesn't exist for the number 5, but it makes sense to represent 5 as 0000005. And so this check here makes perfect sense. We can do a similar check here. But it's not quite as nice because if we're trying to write out of bounds, then there's no way that we can handle that in a logically consistent way, or a way that meets the user's expectations. And so we can avoid writing out of bounds, but this is probably going to lead to some kind of bug or error if we hit this case. So let's make another note to do, make cells automatically grow as needed. Okay, and then we'll say cells index equals val. All right. So I believe that should be most of our big integer class, at least the first pass at writing our big integer class. So now we want to be able to exercise this code. And so we also, in a previous video, created this tests directory where we currently have some code for exercising our primes class. So similarly, we're going to want to add big int test.cpp. And this is going to be mostly just the code that is currently in our problem 16 here. So eventually we'll want a more robust set of tests to make sure that our big integer is working correctly. But for now, we just want a basic sanity check to make sure we haven't made any mistakes. And so we're essentially going to use the code from problem 16 in order to do that. But much of this now has been moved inside of our big integer class. So we can get rid of these. We can get rid of most of these. We'll just need a big int. We'll need to include big int. We don't need any of this. We don't need this. Now we can do write cell. We're writing to cell number 250, and we're writing the value 1. Now I decided to switch this from numcells -1 to 250 because we actually don't care how many cells we have. It could be 10,000 cells. What we really mean to do is write the value 2 to the 1,000th, and that corresponds to writing 1 to cell number 250. Okay, so now here we can say while not n dot 0. We don't have our remainder here anymore. We're not tracking 0 anymore. We're just saying sum plus equals n dot div mod 10. And the rest of this has all been moved inside our class. Okay, so that should essentially be our solution. We do need to do a few updates to the make files to add our new code. So let's go to our tests make file. And we'll just copy that and replace primes with big int. Okay, good. We'll also need to update the make file for our library, so that's under common. And so let's just up here say bigint.o and bigint.o. And again, we can mostly just copy this and replace primes with big int. Okay, great. So let's go into our common directory and make. It looks like we have a couple of problems. So first we're going to need, I always seem to forget this one, that memset requires string.h. And then I forgot that I had renamed this to num big int cells. Oh, and I didn't put the I didn't include this in the big int class. Okay, that looks good. Now I've intentionally made a mistake here to demonstrate there's one additional makefile change that we'll need. You'll see if I do this, we rebuilt our primes test, but we did not rebuild our big int test. And so if we go back to that makefile, the way make works is that if you have multiple build targets like we do here, you have this primes test and this big int test, it will only build the first one by default. And so we would like our default behavior to be that it rebuilds everything. And so we're going to add a new first target here called all. And that's going to depend on both primes test and big int test. And so this will cause either of these to be rebuilt if either of them are out of date. Now there's one problem with this approach, and that is if I were to add a file or a directory called all, this would not work because it sees that all already exists and is up to date, and so it wouldn't actually check or that it wouldn't actually rebuild everything. And so we're just going to do phony all to indicate that this is not a real build target. It's just a kind of a placeholder target. And so now if we go over here and we say make, Yes, we can see that it's already built our primes test, and now by doing make, it's added. You can see here, it's built the big int test. Let's get rid of that backup file. There we go. So you can see here our primes test has been built. Okay. Now there's one more change I want to make to our make file, and that is, in addition to having an all target, we want to have a clean target. Now that we're getting multiple things that are being built, it's kind of tedious every time to have to go and manually delete those. And so we're gonna make another phony target called clean, and that's just going to remove primes test and big int test. So now if I say make clean, you can see that it's removed our the binaries that we built. Okay, so let's make the same or similar changes to our other make file now. So if we go back here, it's not as important that we have a make clean because we only have one build target here. Excuse me, it's not important that we have a make all because we only have one build target. But we do have multiple build products, and so that is, we have these .o files that are also being built. And so let's do .phony clean, and we're going to say rm star.o and libnumtheory.a. So now if we go back to our common directory, you can see our build products there, and then we can say make clean, and we see that the .o's and the .a have been removed, and the source is still there. Okay, great. So now that we've updated all of our build stuff, let's go and see if our program actually works. That's right. I just deleted our library, so it's not going to exist. There we go. Okay, now we have everything built. Let's run our big int test, and we see that we get 1366, which you may remember as the solution to problem number 16. Okay, so our code is working just fine. Now let's get back to some of those to-dos that we wrote for ourselves. So if we go back to bigint.cpp, the first one was up here so that we could optimize our tracking whether our number is 0 or not. And an easy way to do that is that instead of iterating over all the cells every time we want to make this call, we can just track the number of cells that are equal to 0 as we make changes to the individual cells, and then just check that value. So that is, we're going to go back to our bigint.h, and we're going to have this this value here, call it num0 cells. And so we're going to want to initialize that to num big int cells. That is, when we start, all of the cells are 0. And down here, we're going to update num0 cells whenever there's a write. So this is the advantage. You may recall earlier I talked about how even when you're doing internal access to your data, that is, even within your own class, you're writing and reading from cells, it's good to have these accessors so that now this write cell call here will correctly update num0 cells when that write happens. And so we can say, if cells index equals 0 and val is not equal to 0, then we reduce the number of 0 cells. Else, if cells index is not equal to 0 and val does equal 0, then increment num0 cells. Okay, so now we should just be able to do return num0 cells equals num big int cells. And we can get rid of all of this. I've made a minor typo. Okay. Okay, and it still gives the same answer. Great. Okay. So now there's one final thing we have to do before we can call this video complete, and that is to make our cells automatically grow as needed. So you may recall in when we were designing our primes class, we ran into this same problem where we needed an array that would grow automatically. And the solution to that was the vector class. So I've got that pulled up right here. This is just a container that looks a lot like an array, except for you can resize it as needed. So that's what we're going to use to make our cells grow automatically. Okay, so let's go back here. Let's include vector. And then we can just go down here and say std vector uint 8t cells. Okay. And we don't need this num big int cells anymore. We will have to update our code over here. So now when we start off, our cells have size 0. And so we can just set num0 cells to 0. And then we don't even need to zero anything because we have 0 cells. Okay. Now instead of checking against num big int cells, we'll check against cells.size. Let's see here. We'll again use cells.size. Let's see when reading cells, again check cells.size. Okay, and now here comes the interesting part, where if index is greater than or equal to cells.size, then we need to resize our array. And so going back to the vector class here, this is the vector constructor. Let's go to, so this is the vector class proper. And we want the function resize. Okay. And in particular, we're going to call this first variant, which is going to add default constructed elements. That is, for the case of integers, that means zeros, which is exactly what we want. There are options where you can insert a specific value on the end, but adding zeros is exactly what we need, so that's just fine. Okay, so now we're going to say cells dot resize, and we want it to be of size index plus 1. But we also need to update our num0 cells. And so let's see, we're going to, the number of cells that we're adding is just going to be, let's see, index plus 1 minus size. And so we're going to say num0 cells plus equals index plus 1 minus cells dot size. And I believe that should be correct. Okay, so let's see how that works out. Okay, and we have our answer once again. Great. So now we have a big integer class that's capable of division and taking the remainder modulo small integers. The only thing that we need in order to solve problem number 20 now is multiplication. And so that is going to be the subject of the next video. So please look forward to that.